Moving on to page 100, we're going to read and add to our foldable. Regular and diffuse reflection. You see objects when light reflects off of them into your eyes. That's how we see objects. Light is reflecting off of the object and going to your eye. Why can you see your reflection in smooth, shiny surfaces, but not in a piece of paper or a painted wall? The law of reflection applies whether the surface is smooth or rough. That's why it's called a law. Reflection of light from a smooth, shiny surface is called regular reflection, and that's like what you would see up here with our regular mirrors and whatnot. Look at the figure to the right. The 3 incident rays, remember incident is going toward the surface, incident rays, and then the 3 reflected rays, they're all parallel. Okay, the incident rays are parallel, and then the reflected rays are parallel. You see a sharp image when the parallel rays reflect into your eyes. Now, when light strikes an uneven surface, the angle of reflection still equals the angle of incidence at each point. That's the key here, is each point. So every single spot where it hits that rough surface, every single spot, it's still reflecting in a very predictable same angle. It's just that the surface at that particular spot is going to be different in each spot. So that spot's different from that spot. The surface is angled differently. However, the rays still reflect, they do reflect in different directions. Reflection of light from a rough surface is called diffuse reflection. Diffuse reflection. And as you get your foldable, remember our foldable we've been using with the little flaps here. We've talked about electromagnetic waves, light interacting with matter, and now to the law of reflection. We can now add our rough surface. Now I took this diffuse reflection and I kind of turned it on its side to match our mirror over here and then our curved surfaces here as well. So here's our rough surface, and we've got the light rays coming in at a parallel coming in, but at each particular point it's going to bounce off at a different angle. And this is called diffuse reflection. Notice I've also added in regular reflection and diffuse reflection. So you want to add those in. Scattering. When a beam of sunshine shines through a window, you might notice there are tiny particles of dust. You see the dust particles because they reflect light waves. As the figure below shows, dust particles reflect light waves in many different directions because they have different shapes. This is an example of scattering. So we've got all this light coming in and it's bouncing off different particles and going every which way. It really depends on where it hits the surface. Is it going to go up? Is it going to go down? It really depends. Now here's a picture of up in near the Bay Area, near San Francisco. It's called Big Sur, and it's very foggy up there, very, very foggy. And so here's this fog. And so my question to you is, why is it so hard to see through fog? Knowing what you know now about light scattering, why is it so difficult to see through fog? Scattering occurs when light waves travel in one direction and they're made to travel in many directions. The dust particles scatter the light waves in a sunbeam. If there are enough particles in the air, all of the light will be scattered. All of the light will be scattered. That's only if there's enough particles in the air. So when this happens, no light will be transmitted. Now remember that word transmitted? That was back here when we talked about transmission of light. We can see transmission of light through transparent objects and translucent objects, such as clear glass or even frosted glass. Okay, so that's transmission. Now, if there are enough particles, no light will be transmitted, and this is why clouds and fog are considered opaque. Okay, that's our kind of review that vocabulary word, opaque. Once again, I go back to my foldable. In absorption, and we see the word opaque, it means that material that light does not pass through, and this happens through curtains, wood shutters. Basically, no light can go through. So clouds and fog are considered opaque. In fact, water particles in the air, which is what fog and clouds are, they reflect the light, and all the sun's light is scattered, so the cloud appears opaque. The light cannot go through it. All right, what I'd like you to do right now is head back to page 89. That's evidence C in the CER. And what you'll see there is right here. It's called More Evidence. And what evidence have you discovered to explain what happens when light reflects off a rough surface? So you can go ahead, I just copied this from the previous page. Light rays that reflect off a rough surface still reflect at the same angle at which they strike the surface. That's the law of reflection right there. However, light rays do what when they hit a rough surface? How would you describe how a light ray reacts and when it hits a rough surface? All right. On page 101, you'll see some information about retroreflectors. And when you hear the word reflector, what does that make you think of? What does a reflector actually do? So here's some pictures. You see there's a road, and you see there's a bicycle here, a bicycle with this little orange thing here. A retroreflector is a device that reflects light parallel to, but in the opposite direction of the light source. The retroreflector can reflect light back to the source regardless of the angle of incidence. This means that the angle of incidence is 0 degrees. And you're like, well, wait, what? What does that even mean? So, most important part here, green. It is possible to make retroreflectors as thin as a piece of paper because the light will go anywhere. No matter where the light's coming from, it will go in several directions. So why are these so special? Why are these so cool? What is so special about a retroreflector? And you can refer back to this yellow part here. It can reflect light back to a source regardless of the angle of incidence. It's like magic, but it's not magic, it's science. Retroreflectors are used as safety equipment for objects that are difficult to see at night. The surface of roads have retroreflectors to reflect the light from a car's headlights back to the vehicle. This makes road markings able to be seen from all sides. So you'll see reflectors in the road. And so my question to you is, why are retroreflectors so important for nighttime safety? Okay, why is this so good for nighttime safety specifically? More information about retroreflectors. Retroreflectors have even been placed on the moon. There's a picture of the moon for experiments. So scientists point lasers, very big lasers, at the moon, at these reflectors. The light bounces off the reflectors and travels back to the scientists' laboratories. The scientists can measure how long it takes for the light to travel to the moon and back. Knowing how long it takes for light to travel, the distance can then be calculated with very high precision. Perfect precision. This is how we know that the moon is actually drifting away from the Earth at a rate of about 4 centimeters per year. It's drifting away from us. Isn't that crazy? Your turn. So here's an opportunity for extra credit. Please see Google Classroom for details and a rubric for this particular assignment. Retroreflectors are used for many scientific purposes, as well as safety technology. So what I'd like you to do is research one of those ways that a retroreflective surface is used today. And you're going to make a presentation about this and about this surface and its uses. And once again, look to Google Classroom for more details and directions and a rubric for this extra credit assignment.